But before we continue, I want to, some students who came and told me that they did not have any problem with cancelling the Monday lecture, having an extra lecture on Tuesday. Some of those had some reservations, so they said that they have no problem yesterday. So I want to now ask finally, does anyone have a problem with this scheme? What we have now is Monday 8 to 9, Tuesday from 12 to 1 AM, PM, Thursday 11 to 12 noon, and Friday 10 to 11 AM. Right? So now, current. What I'm proposing, I want to make sure that everyone is in agreement. There should be no confusion because attendance does have some weightage in this course. Right? So Monday cancel no class. Tuesday would be 12 noon to 1:30 PM, and Thursday and Friday remain the same, with no change in that. So all I am saying is that there will be no class on Monday, but it will be compensated by an extended class on Tuesday from 12 noon to 1:30 PM. Does anyone have a problem with this? This is the final call. If yes, then you have to raise your hands now. Right? If you are afraid of being lagged outside the class, you are a lone person or not, that I cannot, you have to take that chance, right? But still, you have to compare and what are the consequences of accepting this and not accepting this. That is your decision. If you have a problem in terms of class, because it's going against the institute schedule, and I normally do not wish to do that. So I have no problem, I have no stake in this change. My day begins at 3:30 in the morning. So for me, even every day 8 o'clock class is perfectly fine. So if anyone has a problem with this, then we'll go back to the old one. There's no problem, right, for anyone. So this is now, and this is, of course, 11 to 12, that remains as it is. Thursday, Friday, there's no change. Tuesday, we meet next Tuesday, so we won't be meeting next Monday. So this will start from next week onwards. Right? So there will be no class on Monday. Tuesday you have to prepare to have an extended class up to 1:30. Right? So in that, we'll continue with the usual lecture. What we have seen so far are the three hypotheses of Stokes. One, right, that the D is a function of the deformation tensor, and then we went and discussed or defined the deformation tensor. The deformation tensor is nothing but the symmetric part of the velocity gradient tensor. So the velocity gradient tensor can be written as D plus omega. So D is a symmetric part. So we said any matrix, in fact square matrix, can be split into a symmetric part and an anti-symmetric part corresponding to that matrix. So that would be, the D would actually be half. Let me make this explicit. And the omega would be half have to write the ijth element of this. There was some confusion because in one of the derivations it looks like I made a mistake in substituting the ijth element of omega. So let me clarify this. So first of all, you have to understand the ijth element of is dbj by dxi by our definition. That is how I have chosen to define it. Right? You can also, some books also follow the alternate one of dbi by dxj. So we are not following that. So this is clearly dj comma I. That you have to understand. Right? So I don't want you to be confused with these indices. So dij then becomes half times, simply I just follow this, bj comma I plus bi comma j. Take the transpose of the ijth element, then I get the ijth element of dij of d rather, and this would simply be bj comma I minus bi comma j. I think the problem was when I was, let me go to what we covered yesterday. What I pointed out was that if, in fact, I have two material points which are separated, let's say, by x and x plus dx, then we showed that, so this is the vector dx, we showed that d by dt of ds square, the ds square is dx dotted with dx, the square of the length of the vector dx, right, is given by 2 times dx dotted with d dotted with dx. Right? So now, towards proving this, the first step was to prove that this is actually equal to what was this initially proved to be equal to. We proved that this is equal to 2 times dx dx, right? And then this is equal to this. In between we prove that dx dotted with omega dotted with dx is actually equal to 0. We proved that. So I think that is where one of you pointed out that I made a mistake in that, because I wrote this as dxj omega ji dxi. There is no problem. I have to prove that it is 0. So there, by substituting, I should have substituted the ji element of omega. Probably I substituted the ij element. Right? So actually you have to correct it. So this would be dxj times was half, right? Omega ji is obtained by simply interchanging I and j in every term. So this would be I comma j minus b j comma I dxi. So final proof is the same. It won't be affected because what I have done is just a negative of what I should have substituted. Since anyway it is going to be 0, the proof that this is equal to 0 can be easily shown. That is not affected. Final result is not affected. This intermediate step you have to correct it. Another point I want to clarify, when I wrote, for instance, dx, I also made a somewhat casual remark about the time not coming into the picture. Right? But actually, the time does not come here into the picture because actually the dxi, we are considering the dxi is the difference, right, between the ith coordinate of x and x plus dx at a given time t. So there is no reason for the time to come in the differential, because I pointed out that xi, for instance, is xi psi t. So when asked, when you take the differential of xi, should not there be a term which has the change with respect to time coming into the picture? that is not, what we are actually looking at is this dx. This dxi is nothing but xi of psi plus d psi t minus xi of psi t. So both correspond to the same instant of time, 2 points, the same instant of time. So there is no reason, in fact, for the time to come into the picture. But by my comment, I made it appear as if it's there, but I am just focusing on the variation with respect to psi. That's not quite correct, right? Actually, there is no need for me to have any additional term here, because I am looking at a change which represents the change in the I coordinate of two material points at time t, right? So there is no need for any term with respect to variation in time. With those two clarifications, yes.
And we can say that the two bodies are different because at the same time.
Bodies, it's not two bodies, it's 2 points, right? Which are related to whose this is mapped onto the material coordinate psi. This is mapped onto the material coordinate psi equals d psi. So I am denoting the position of this by simply x plus dx. So what is this dx? That is actually determined by this. Right? So that's all there is to it. There's no need for any confusion on that. So having clarified that, it is pretty much done with this. So the main point here is that what this indicates is that the anti-symmetric part of the velocity gradient tensor effectively corresponds to a rigid body rotation, because of the relative distance between 2 points does not change with time, right? Then that effectively corresponds to a rigid body rotation. And so this is the actual effect of the deformation is contained in D. So the velocity gradient tensor does represent a measure of the rate of deformation. But however, when you split it into a symmetric and anti-symmetric part, we find that the anti-symmetric part has no contribution at all to the rate of change of distance between 2 points. So we conclude, Stokes concluded that the entire effect of deformation is actually contained in D, and the stress has to be related only to D, and the omega doesn't come into the picture, right? So that is the main significance of the first hypothesis of Stokes. Then we also said that we went back to discussing the rigid body rotation. They pointed out the rigid body rotation as a scalar omega, which is the rate of change of the angle, right, of associated with the rotation. And then you have a vector which is given by the scalar multiplied by the unit vector corresponding to the direction of the axis of rotation. And then we can also associate an anti-symmetric tensor with that. An anti-symmetric tensor with that. The idea is that the anti-symmetric tensor has 3 independent components. And this also, any vector has 3 independent components. So I can replace the effect of the angular velocity vector by an anti-symmetric tensor, second order tensor. So then there are many different ways of representing this. The one I chose, of course, there's no choice to the diagonal elements, they have to be 0, right? As far as the off diagonal elements are concerned, we chose this to be omega 3. So once I've chosen this, this automatically becomes minus omega 3. This becomes minus omega 2, and this would then become omega 2, omega 1, minus omega 1. With this choice, it's easy to show that an arbitrary element of omega ij, the tensor, is given by epsilon ij omega k, and an arbitrary component of the angular velocity vector is given in terms of the tensor by half. Now it is easy to see that immediately that the diagonal elements of this are 0, because the diagonal elements would mean I equal to j, right? And if I put I equal to j, it will be 0. So here I am not referring to the sum of the diagonal elements, omega I, that is also 0 in this case. We take a particular, put j equal to I, no sum implied, I am referring to a particular element, diagonal element. So I put I equal to j here, right? Automatically it will become 0. Because by the property of the epsilon, if any two of the indices are equal, it is 0, right? So all the diagonal elements are 0, we can easily verify. I can take, let us say, if I want to take omega, let's take one of the negative ones, omega 1, 3, right? So I put I equal to 1 and j equal to 3. So whichever way you look at it, there's a sum v over k, right? So that means actually there is no sum at all. If you're looking at the off-diagonal elements, because I and j are automatically different, right? So two of the indices are chosen. So k cannot be equal to any of the two indices chosen. So the only choice is whatever you have not chosen, right? So for omega 1, 3, the only term that would contribute, right, is k equal to 2. So that would be epsilon 1, 3, 2, omega 2. Which is 1, 3, 2 is minus 1, so minus omega 2. So you can easily verify the other elements if they are matching with this formula. Coming to this, I can take any one, put k equal to 1. Now this is the sum over I and j, because I am choosing only k. So I and j are open to two choices, right? So it will be a sum over I and j, probably having two terms. Let's take omega 1. That will be half k equal to 1. So half eij1 omega ij. Now I can be either 2 or 3. If I is 2, j has to be 3. If I is 3, j has to be 2. Right? So this will be half epsilon I equal to 2, so j is 3, 1, right? So I equal to 2 means 2, 3 plus half epsilon, then y is equal to 3, 3, 2. Which is equal to 2, 3, 1 is 1. So omega 2, 3 you see is omega 1 plus half times 3 to 1 is minus 1. Omega 3 2 is minus omega 1. So the net effect is omega 1. So all I have to do is that it matches, right, with there's a perfect correspondence between the tensor and the vector. So one can be expressed in terms of the other. That's all. I just verified the formula written. You know, how did you arrive at this formula? The formula is given. It is not difficult to verify that it is in fact correct. Right? So these are compact. These will come in handy, right, when you're doing the manipulations involving omega ij, right? So the one exercise which I leave it for you to do, and we can discuss it in the next class, is to prove now with omega given by this, because here what I have said is that given the vector, I can construct a tensor like this, but here actually what I have given is the omega that is given by this, right? And so I can ask what is the vector corresponding to this. So you can show that in fact is actually actually equal to half times the curl of the velocity vector. I'll leave it as an exercise for you to prove. For that, of course, I have to make use of this. That is why those relations are useful. So I can take an arbitrary kth component, and there I have to substitute this. Then you can easily prove that that is half times the curl of the velocity vector. So I'll let you try to prove it, and if there is a problem, we'll discuss it in the next class. So are there any questions from this? So we go to now the second hypothesis, like the first two. Isotropy or no preferred direction in space. Both are somewhat vague and difficult to comprehend. But to understand that, what we have to look at, what it really means is the effect of these vectors and tensors and the transformation of coordinates. Right? So we discuss the general transformation of basis is what I should say. So now to understand this, I can consider this as a simple two-dimension. Let's say I have two axes I can represent. Right? Now suppose I didn't have this coordinate system and I want to fix the location of a point on the board, let us say. Right? So then, I have no way of fixing it properly. Right? So I need to choose a coordinate system. So I can choose an origin and then choose. This is how we typically locate points on the plane. Right? You draw a graph xy, right? And the point is represented by coordinates. You don't say the point is lying on, in the middle of the board or something like that. That's very difficult, not very quite precise and easy to use. But you have to fix a coordinate system. Since we are dealing with vectors, I can simplify the discussion by associating with each point on the board a vector directed from the origin. So this would be one vector. So now I will say that what I am saying is that I can either talk about points or with each point I can associate a vector which is obtained by drawing a directed line segment from the origin to that point. So we have P1, let's say, P prime. When I have P, maybe not, I won't introduce that. So now I can talk about the location of the point or the components of the vector with respect to the chosen coordinate system. Right? So that I can easily obtain by simply projecting from P onto the axis. Right? And I will say that this is, let's say, xp, right? And this would be yp. So I can represent the point by xp, yp. Or I can represent the vector OP by xp I, or rather E1 plus, maybe I just call it x1 here. x1, x2. Right? Because I call it O1, so I call this x1 and x2. I can write it like that. Right? Either in vector form as a vector, right? So it has a component x1 with respect to the basis vector E1. So E1 is the unit vector along this, and E2. Now suppose I consider a different coordinate system or a basis system which is merely the original set of axes rotated by a certain angle, let's say. So now I'll consider new about 1 prime, and for simplicity consider them also to be perpendicular to each other. So if they rotated by an angle, both 1 and 2 will get shifted. Right? Now clearly, even though the point I'm talking about is the same, P, or the vector I'm talking about remains the same, OP, I can now ask clearly what are the coordinates of the point P, the same point, with respect to the new basis or the new coordinate system, right? Or what are the components of the vector OP with respect to the new basis vectors. So now this becomes, the unit vector here becomes E1 prime, and this would become E2 prime, right? So clearly the components would be different. So it's the same vector, right? But having different components with different basis vectors. So now I can generally consider, right, going away from the geometry, because once you go to 3 dimensions, right, it's difficult to represent this geometrically. So in general, you would have even considered an n-dimensional space. I can consider 2 basis set of vectors, E1, or let's say the prime and 2 bar. Now I'm generalizing to an arbitrary dimension. Finally, we'll be using it for 3 dimensions only, because these results are valid for arbitrary dimensional, finite dimensional vector spaces, which certainly you would have encountered in your mathematical methods course, at least those who have taken it. Right? So now I can ask what are the coordinates or the components of a particular vector x. So we don't really, now you can ask, well, is there an identity to the vector itself? So there's no unique identity to the vector other than its representation with respect to particular coordinate system. So whenever I say x1, x2, x3, x4 and so on in the n-dimensional space, or x1, x2, x3, there's always the implicit assumption that it is only with respect to a particular chosen basis set of vectors, right? So if the basis set changes, the same x vector will be represented by a different set of components. That's very clear from this geometric picture, right? So the same vector x, I will say, has components with respect to this basis set, or it could have components. Bar I'm choosing because this is what Alice follows. So if you have one reference to consult, you don't understand what we are discussing. So we have this. Now there's a very general way of representing how x1 and x1 bar are related, how the components in one coordinate system or with respect to one set of basis vectors is related to the components in any other basis set, right? So now I can write that down. It's possible to show that x bar, right, is given by L bar, a matrix L bar times x, and x in turn is given by L times x bar. So by x actually I mean with respect to the original, I can choose this as my original basis set. So I will call that as x, the way we have called it all along. Only now I am generalizing to n dimensions, right? So the modified one, I can choose this also as the original and this is modified. That doesn't, there's nothing special about my original basis set. I'm just choosing one basis set of vectors, right? So this is the relation between the components of x in the new basis set with respect to it in the original, and this is the reverse, because there's a one-to-one correspondence between the components, right? So now Lij, the matrix ij element is given by Ei dotted with Ej bar and Lij bar is given by Ei bar dotted with Ej. This can be easily proved, but I don't expect you to remember this. But this is a general way of representing how the components of the same vector in one basis set is related to its components in another basis set. That's how you have to remember. Special formula are not really required for the purpose of this course. But here I have assumed that this is an orthonormal basis. The whole distinction is valid only for it is valid for arbitrary basis sets which may not be orthonormal. Orthonormal means what? Ei dot Ej is equal to delta Ij. Right? That means each vector is orthogonal to any other vector, and the length of each vector is unity. That's an orthonormal. That's what we have always been considering, the three-dimensional space. Now, in this case, it's possible to show that L bar is actually equal to L inverse, and it's also equal to L transpose. And we choose basis sets which are not orthonormal, let us say, then these relations will remain valid, but these have to be modified. And also, this part will not hold. So for a matrix for which L inverse is equal to L transpose, that is often referred to as an orthogonal matrix itself. When we are taking the transformation from one orthonormal basis set to another, which is what we will restrict ourselves to, then we will find that this transformation matrix L inverse is actually equal to L transpose. That's a property of what are known as orthogonal matrices, right? So now, this is what we have. Now we have looked at vectors now, how they transform. What about tensors, which for us now will restrict to second order tensors alone, right? But however, more generally also, you can consider arbitrary dimensional matrices, but there what we will consider are matrices operators acting on vectors, right? For instance, if I have a vector in n-dimensional space and I, let's say, pre-multiply it by a matrix, an n by n matrix, right? Then I get another n-dimensional vector. But of course, if you can also consider transformation from different dimensional spaces. If, for instance, I multiply n by 1 vector by m by n matrix, right? I will get from an n-dimensional vector, I will generate an m-dimensional vector, right? So I will consider a general matrix as going from V to U, for instance, right? So V can be, let's say, Rn, this can be Rn, right? And so A would have a representation as would be of the form m by n. So that when it acts on an n-dimensional vector, it will give an m-dimensional vector. But here, I am going to consider only going to be to B. And for simplicity, I will simply consider R3 to R3, even though the arguments are valid for arbitrary n-dimensional spaces. So we can now restrict ourselves to simply even E2, E3, focus on 3-dimensional space, even though the arguments are valid for arbitrary dimensional spaces. And then we won't really talk, if you have n-dimensional matrices, then we won't really talk about them as second order tensors. That will not hold anymore. So I am restricting myself to this 3-dimensional. So now, just as the same way you can say that a vector, right, requires specification of the basis set, the tensor, which in this case I know regardless as a second order tensor, also, right, would depend on what basis set I choose. For instance, what is the first inherent second order tensor we encountered? The stress tensor. It was given by n dotted with t is equal to t. Now what the discussion there says is that depending on my choice of basis set, both n1, n2, n3, I can choose one basis set, and this will be t1, t2, t3. Right? With respect to, let's say, e1, e2, and e3. Now if I choose, this is for e1, e2, e3 basis set. Right? Now if I choose e1 bar, right, then obviously this would be n1 bar, n2 bar, n3 bar. This would be t1 bar, t2 bar, t3 bar. So those are all vectors, and we have seen that they will clearly transform when you choose a different basis set. Right? So you obviously expect the stress tensor, the components of the stress tensor also to change when with respect to the particular basis set that is chosen. So this one had Tij, arbitrary ij there. This is going to have Tij bar. Now we can ask how the elements of Tij are going to be related to Tij bar or vice versa. Right? It's possible to show that T bar is actually given, where I have defined the L there, is actually given by L inverse. In general, it is to be given by L inverse. But because we are talking about orthogonal transformation, it can also be written as L transpose L. That is how it will transform. So the same matrices L and L inverse and all the L transpose will come into play. I have already defined them here. Only now they run only from I equal to 1 to 3 and j equal to 1 to 3. Actually, the whole discussion can be framed for an arbitrary finite dimensional vector space. Since our interest in this course is going to be 3-dimensional, we are restricting only to the 3-dimensional case, but pointing out that the discussion can be extended to more general cases. Right? So this is the basic expression for how the components of a second order tensor would transform under a change of basis set. Right? So I wanted to prove this. Now I can make it very concrete what is meant by isotropy, or there is no preferred direction in space. All it means is this. It means that what do you make out of this now? Does the principle of isotropy is any clearer? No, it's certainly more concrete now, rather than simply saying there is no preferred direction in space, which I don't know what it means to you, doesn't mean anything to me. We are replacing it by, you look at the way what Stokes implemented, and this is exactly what is the summary of that property of isotropy. So what do you infer from this? What has changed and what has not changed between the first and second expression?
Change of basis.
Change that has changed, but there's something that has not changed in the two equations.
Still a function of D. It's still a function of D. Still a function of
how many symbols you see in the first equation? 3, T, F and D. Right? So what has changed and what has not changed? F has not changed. The functional relation that relates the components of the stress tensor to the deformation tensor does not change under transformation of coordinates. So what Stokes' second hypothesis essentially means that this functional relation is independent of our choice of coordinate system, which is what you expect actually intuitively, right? Because I can choose any coordinate system I want, and if I choose one, I will get E1, E12 and so on, right? And similarly, now we have already seen, based on this, the same thing would apply for T also, right? So when I choose, somebody else chooses a different coordinate system, they are going to get, for the same stress tensor and the deformation tensor, they will get different values of the components of the tensor, right? But what Stokes' hypothesis says is the relation between T and D, which is determined by the particular form of the function, that will not change no matter what coordinate system you use to represent the tensors. Right? So even though the actual elements of the stress tensor and the deformation tensor will change, obviously on change of coordinate system or change of basis set, both are the same. Right? However, the function that relates T to D will not change. So it will have the same functional relation, right? No matter what coordinate system you choose. Now, the third hypothesis we have already seen, that is easy to when D equal to 0, right? That means when there is no deformation, the nature of the stress tensor should be such as to represent the nature in when the fluid is at rest, that is the hydrostatic stress. Now, the important thing which we are not going to prove, the consequence of this, as I said, is that necessarily the stress tensor has to have the following form. It has to have alpha times plus beta times E plus gamma times E squared. Where alpha, beta and gamma are not necessarily constant, but they are functions of the invariants. That is something that I have to explain. What do I mean by invariants? Right? The scalar functions are the invariants of D. What do you understand by invariants of a matrix? This is again valid for any n by n matrix. What do you mean by invariant? Invariant with respect to what? That at least you should be able to answer. With respect to change of basis. Every matrix has certain, the elements are going to change, but there are certain properties associated with the matrix, right, that will not change on transformation of coordinates. So now you have to understand, you solved innumerable number of problems involving matrix. You should understand when a matrix is given to you as matrix A, it effectively represents the elements of a second order restricted terms is a 3 by 3 matrix, right? It represents a tensor with a particular chosen coordinate system. So the same tensor can be represented. We have never considered this point, right? But just as a vector can change its components with the change of coordinate system, so also the components of a tensor can change, right? So when you're given a matrix, it only represents a tensor to one particular coordinate system. So can you name one invariant of a second order tensor or in general n by n matrix? One thing that will not change under transformation of coordinates. Trace of a matrix, the determinant of the matrix will not change. These are called the invariants, and for a 3 by 3 matrix, there is one other invariant that I will write down in the next class. But you will find very importantly that if I have an A, which is a 3 by 3 matrix, I can talk of an eigenvalue problem for the matrix, right? So now the eigenvalue equation called as a characteristic equation, you will have, I can make the first coefficient 1, so this would be the second coefficient will have something, right? The third coefficient will have something, the fourth term, right? This will be the determinant of the A. This is probably the trace. This will be something else. Possible to show that all three of the coefficients of the characteristic equation are invariant under transformation of coordinates. We see the significance of this. This is what I mean by invariance of D. The invariance of D are the trace, the determinant of D, and this other coefficient that I will write in the next class. So with this we have to stop. So we meet again on Tuesday. Are there any questions? Quick questions, because we've run out of time. Or questions which have a quick answer. Okay, those of you who have somewhat elongated questions, have answers that require elongated answers, can stay back. Others who have to leave, let me see. We'll meet again, I emphasize on Tuesday.